So let's solve the problem. Y double prime plus 2y prime plus y equals to t with the condition that when t is 1, the value of the function y is 0, and when t is 1, the derivative of the function is also 0. Now we are going to solve this problem by use of Laplace transform methods. So let's see how to solve such. So the problem is to solve now. Remember, this differential equation solution can be written as d squared y dt squared plus 2 dy dt plus y equals to t with the given conditions that the value of the function at t equals to 1 is 0, and also the derivative of the function at t equals to 1 also 0. Now, to be able to use Laplace transform method, we expect our initial conditions to be at t equals to 0. But since the conditions given do not allow us to start at t equals to 0, we are going to introduce a new variable or to do a transformation that is going to change the whole differential equation to take the structure of initial conditions starting at 0. So we let a new variable u be given by t minus 1. Now, what is prompting us to say let u to be t minus 1 is because when t is 1, then we'll be assured that our new variable u will be 1 minus 1, which is 0. So therefore, if our differential equation is in terms of this new variable u, it will allow us to use Laplace transform method because we'll be starting at 0. So this transformation, then this means that t or du is the same as dt, and this is the same thing as saying t is the same as u plus 1. So then now we change the integral, the differential equation from being with respect to time, but with respect to this new variable u. So this is the same thing as saying du dt is the same as 1. Now, dy dt by chain rule, the same as dy du times du dt. So then this means that dy dt is the same as dy du times du dt, the answer is 1. So which means dy dt is just the same as dy du. So where there's dy dt, we replace by dy du. And then the second derivative of y with respect to time is the same as d dt of dy dt, just from definition. But we are saying that dy dt is the same as dy du, so it's the same as d dt of dy du which is the same thing now. We can always switch this du dt and write it as b du dy dt. We can always switch when we have these two operators. So dy dt still is the ui du. So du, then replace this one by dy du, which are the same as d squared y du squared. So we have successfully now gotten the replacements for both the second derivative in terms of t, the first derivative in terms of t, and then this value y in terms of u. So therefore, if I call this one question 1, I'll say 1 becomes d squared u y du squared plus 2 dy du plus y equals to, where there's t, we replace by u plus 1. We'll have u plus 1. So therefore, we have successfully replaced our converted our differential equation into this new variable u. So then now, with this new differential equation in terms of u, the initial conditions now starts at 0, because now when u when t is 1, as given in these initial conditions involving time, then the value of u is 0. So therefore, our differential equation will be this, with the initial conditions, that y at 0 is equals to 0, and y prime at 0 is also 0. So remember that now in this case, this is y in terms of the new variable u. Now we let L of y be the Laplace transform of y. And then from definition, the Laplace transform of the derivative dy du will be given by s y of s and then minus y at 0. So which will be just simply s y of s, and then y at 0 is 0, so just be given by this. And then the Laplace transform of the second derivative of the function will be given by, from definition, is s squared y of s minus s y of 0, and then minus y prime at 0. And then replacing by the values we have in the differential equation, we simply have s squared y of s. This is minus s times 0 minus 0. So which will just be s squared y of s. So then now, using this, if we call this one number 2, then taking Laplace transform on both sides of 2, we get a Laplace transform of second derivative of y with respect to u plus Laplace transform of 2 dy du plus Laplace transform of y equals to Laplace transform of t, Laplace transform of u plus 1 so u plus 1. Now from definition, these values we have defined at this point, a Laplace of y, Laplace of the first derivative, Laplace of the second derivative, we'll get s squared y of s plus twice s y of s, and then plus y of s. Now Laplace transform of this sum is simply the same as Laplace transform of u plus Laplace transform of 1, and Laplace transform of u is the same as one over s squared, and Laplace transform of 1 is the same as 1 over s. So on the left-hand side, we factor out y, which is common. So we'll have s squared plus 2s plus 1 times y of s is given by putting over 1 LCM, we'll have s squared 1 plus s. And then we make the y of s the subject. And remember this s squared plus 2s plus 1, this quadratic expression, product is 1, sum is 2. So numbers 1 and 1. So it's like we have s squared plus s plus 1. So common is s plus 1, and then plus 1 into s plus 1. So this is like we have s plus 1 squared. So at this point, s plus 1 squared times y of s is given by 1 plus s over s squared. And when you make y of s the subject, then you'll get y of s is given by 1 plus s over s plus 1 squared times s squared. And you see at this point, this will reduce this one by 1. So we'll have 1 over s squared into s plus 1. So which means that y of s is given by 1 over s squared into s plus 1. Now to be able to get y of u, we now find the inverse Laplace transform of this equation, but then we need to decompose into partial fractions. So this is the same as a over s, b over s squared, and then plus c over s plus 1, which will be given by y of s equals to a into, so when you put everything over the same LCM, we get s squared into s plus 1. So s into this LCM will be s times a times s plus 1 plus b into s plus 1 plus c s squared. So this is the same thing as what we had as s squared into s plus 1. Now, this means that s plus 1 plus b into s plus 1 plus c s squared is the same as 1. So we are interested now solving the values of A, B, and C. So when S is 0, then we'll have 1 equals to B. So the value of B is 1. Now when S is 1, we'll get 1 equals to, so 1 times A is A, 1 plus 1 is 2, and then plus, when I put here, okay, let's say S equals to -1. So this A and B terms will not be into the equation, and so we'll get the value of C. So we'll get -1 squared is 1, so 1 is the same as C. So C is also 1. Now, when you replace, say, S for 1, as we had said initially, then we get that 1 equals to A into 2 plus 1 plus 1 is 2, so 2B. And then 1 squared is 1, then plus C. But we have already solved for B to be 1 and C to be 1, so which means 1 equals to 2A plus 2, but B is 1, and C is also 1. So 1 equals to 2A, 2 plus 1 is 3. So 2A equals to 3 from 1, which is -2. So this means that A is -1. So therefore, capital Y of S is the same thing as 1 minus 1 over S plus 1 over S squared plus 1 over S plus 1. So taking the inverse transform on both sides, so we get inverse of -1 over S plus the inverse of 1 over S squared plus the inverse of 1 over S plus 1. So the inverse of -1 over S will give us -1 plus the inverse of 1 over S squared will give us U plus the inverse of 1 over S plus 1 will give us e raised to power -u. So this will give us our function in terms of the new variable u. But since u was the same as t minus 1, then the solution y of t will be given by -1 plus t minus 1 plus e raised to power -t minus 1. So which means that the function or the solution in terms of the variable t will be given by -1 plus t minus 1 and then plus e raised to power 1 minus t, which is y of t is equals to -1 minus 1 is -2. So I can write this one as e raised to power 1 minus t and then plus t and then -2. So therefore, this is a required solution for the given problem. Now, note that sometimes you may be given same differential equation So to say a d squared y dt squared plus b d dt dy dt plus c equals to, say, a function of t with the initial conditions y of alpha equals to, say, 0 and y prime at alpha equals to 0. When you are given such, you'll still do the same transformation, that let a new variable u be given by t minus alpha, and then proceed in the same fashion. Once you define the formulas for Laplace transforms of the function and the derivatives, after ensuring that you are starting at 0 in the new variable, you should be able now to get the solution to that, to such kind of problems. So always remember that for us to apply Laplace transforms to solve the differential equations, our initial values should be 0. So when the initial values are not given to 0, then you have to transform your differential equation into a new variable that will ensure that you are starting at 0 and then proceed in the usual way. Thank you.